In the last few classes, we've been talking about this general Hilbert space formalism. And in particular, we've talked about the significance of Hermitian operators and about how an operator like a matrix can be Hermitian. And if so, then it has a set of eigenvalues and eigenvectors. And I've talked about properties of the eigenvalues and eigenvectors. So now I want to apply all that kind of theory to quantum mechanics and see, some of the consequences for quantum mechanics of having, all this formalism set up. So there are a few kinds of applications, and what I want to begin with is what the textbook calls the generalized statistical interpretation of quantum mechanics. So you remember in this semester, we've talked about a couple of different ways that that probability enters into our ideas about quantum mechanics, right? So right from the beginning of the course, we talked about a statistical interpretation of the wave function. Right, to say that the wave function magnitude squared makes a certain probability density. And that tells you the probability of having a particle at a certain place at a certain time. Right? And then later on, we talked about how a particle can be in a combination of special states, the energy eigenstates, and then the coefficients of those energy eigenstates in the wave function, those coefficients, magnitude squared, are the probabilities of having the particle in a certain energy state. So now let me say those statistical ideas in a general way, using this idea of inner products and so forth. Okay. So suppose we have any observable. So again, like the textbook, I'll call it Q. Okay. And so this might be energy, it might be position, it might be momentum, it might be anything else. Okay. So we already talked about how we can expand the wave function as a linear combination of eigenstates. Okay, so we'll expand the wave function in eigenstates of Q. So that is, we'll write it as psi is the sum of a coefficient Cn times Fn, where Fn is an eigenstate. That means that Q acting on Fn is equal to little q sub n times Fn. Okay, so the little q sub n, this is the eigenvalue, and this Fn is the eigenstate, or the eigenfunction, or the eigenvector. Okay, and then we talked about what are these coefficients, right? And we figured out that the CNs are the inner product of Fn with psi, right? Okay. And so Q has this set of eigenvalues and eigenstates. Okay, so we could say the spectrum of Q is the set of all the Qn eigenvalues. Okay, so these are things I told you already, right? I think so. Okay, so now the point is, suppose you measure Q. Okay, so you're going to make a measurement on this quantum mechanical system. Okay, and the question is, what can the outcome of the measurement be? And the idea in this generalized statistical interpretation is you will get something from that set. Okay, exclamation point. So that means this set of eigenvalues, this is the menu of possibilities. Okay, if you make a measurement, you're going to get something from that menu. You cannot order something that's not on the menu. Okay, so you have to get one of these possibilities, right? So if Q is the energy, for example, then we have some list of energy eigenvalues. Those are the ENs that we've talked about a bunch of times, right? If you make an energy measurement, you're going to find one of the things on that list, okay? You're not going to get an in-between number. It's got to be one of the things from that list. Okay? So that doesn't mean that the average is going to be one of the things on that list, right? Because if you sometimes get one item from the list and you sometimes get another item from the list, the average might come out to be in between. Okay, so the average doesn't have to be on the list, but each individual measurement has to be one of the things on the list. Okay? And the same for position or momentum or anything else, right? That if there's a list of possibilities, if you make a measurement, you're going to get one of the things on the list in each individual measurement. The average might come out to be in between things on the list, but the individual measurements have to be on the list. Okay, then you could say, well, what is the probability of getting each of those things on the list? Okay, and so the answer is that whoops, how do I do it? You will observe the value Qn, say, you will observe the value Qn with probability of the equal to the magnitude of Cn squared. So that means the magnitude of the inner product squared. And maybe an intuitive way of saying this, a kind of partly intuitive way of saying it, is that the psi is made out of the FNs. The FN functions. And Cn tells us how much of the FN ingredient is in psi. That's not a rigorous statement. That's just kind of a hand-waving way of saying it. Okay, so let's see what examples of that are for example, energy. Okay. So for example one, we could say for working with the Hamiltonian. Okay, so if we have the Hamiltonian operator, H, okay, with H acting on psi n equals the energy En times psi n, right? So this is the time-independent Schrodinger equation, and this is what we have solved a bunch of times in chapter 2. Okay, so then if you measure the energy, then you observe one of the things on the list of energies. Okay, and so you observe the energy En with a probability which is the coefficient Cn squared. You already knew this, of course. This is what we talked about in chapter 2, right? And this is on one of the previous homeworks. Okay, so I'll say you knew this from chapter 2. Okay, and then we could say the expectation value of the energy is the sum over all the possible n's of Cn magnitude squared times En. So this quantity doesn't have to be on the list of energies, right? But each individual En is on the list. Okay, now what about if it were position instead of energy? Okay, so let's say we have example 2 would be the position operator x hat. Okay, and from the end of the class, the last class, I talked about what are the eigenvalues and eigenfunctions of the position operator. So I'll say we showed this. I don't know if I showed it very clearly, but let's show it again. That the X operator acting on eigenfunction Fn is equal to the number Xn times Fn. And this works if the eigenfunction Fn is a Dirac delta function, which is a spike concentrated at the position Xn. Okay, and so if I have, if Xn equals 1.5 centimeters, right, then this function is a spike. Fn is a function of x. That's a spike at 1.5 centimeters. Okay. And if I take this function and multiply it by x, I get 1.5 centimeters times this function, right? Because right here, I'm multiplying the function by 1.5 centimeters. Everywhere else, it doesn't matter what I'm multiplying it by because it's 0 anyway, okay? So this function times x equals this function times 1.5 centimeters, because the only place where it matters when I'm multiplying it by is right here at 1.5 centimeters. Okay. So that's what it means to say that this is an eigenfunction, okay? And the eigenvalue is 1.5 centimeters. So that works at any position, not just at 1.5 centimeters. Okay, and so now we'll say, what happens if you measure position? If you measure position, you get the result xn with a certain probability. And what's the probability? Okay, the probability is Cn squared, which means the inner product of Fn with psi squared, which means, well, let's do the integral to find the inner product. Okay, so that's the integral from minus infinity to infinity, Fn complex conjugate. Okay, so that's delta of x minus xn. I could say complex conjugate, but it doesn't matter because this delta is real, okay, times psi of x and t dx. So it's that integral magnitude squared. Okay, and now I can do this integral, right? The integral is not very difficult because it's an integral of a Dirac delta function times something, okay? And the result is the something evaluated at the position where the Dirac delta function equals, where the argument of the Dirac delta function equals 0, okay? So that means it's the stuff that multiplies this delta function evaluated at x equals xn. Okay? So that is, here's the stuff that multiplies the delta function, okay, evaluated at x equals xn. So that is, whoops, sorry, typographical error. That is psi evaluated at the position xn at time t, magnitude squared. Well, this then, it just comes down to the statistical interpretation that we had at the beginning of the semester, right? I'll say, you already knew this from chapter 1. Okay, so this is telling you that, you know, this wave function squared, magnitude squared, evaluated at a certain position at a certain time, that gives you the probability that you'll find the particle at that position at that time. Okay, so this then you know, is a way of seeing that the generalized statistical interpretation is consistent with the old statistical interpretation, with the original interpretation that we had at the beginning of the semester. Okay, so it works for position and it works for energy. Okay, so if it works for position and energy, how about momentum? Let's go for that. Okay, so let's say now example 3 is for the momentum operator B. Okay, so we have this family of momentum eigenfunctions that we talked about last time also, right? And so we showed that we have this family of eigenfunctions which have the form of 1 over root 2 pi e to the I kx. Okay, and so it's e to the I kx. That's the complex exponential, which is necessary so that the momentum operator acting on this will give just h bar k times this. Okay? And so this is h bar k times the function 1 over root 2 pi e to the I kx. Okay, and this factor of 1 over root 2 pi, this was just what's necessary for the delta function orthonormality. Okay, so this is the eigenfunction, eigenstate. This and this. And this is the eigenvalue. Okay. And then the delta function or delta function orthonormality is this statement that the inner product of 1 over root 2 pi e to the I kx with 1 over root 2 pi e to the I k prime x is delta of k minus k prime. Okay, so now the generalized statistical interpretation tells us if you measure the momentum, you will observe the momentum is h bar k with a certain probability. And that probability is this coefficient magnitude squared, which is the magnitude squared of an inner product. That is 1 over root 2 pi e to the I kx with the wave function psi. That thing squared. Okay, so now let's work out what this inner product is. Okay, so this is the magnitude squared of an integral over x. So 1 over root 2 pi e to the minus I kx. Remember, we have the complex conjugate of the first thing when we do an inner product. Okay, and so the complex conjugate changes this e to the I kx to this e to the minus I kx times our wave function psi of x and t integral dx. Okay, so now we look at this thing and say, oh, this whole thing is the Fourier transform. This is the Fourier transform of the wave function. So this is what we were earlier writing as a phi of k times t, magnitude squared. Okay, so this tells us then about the physical interpretation of the Fourier transform of a wave function, that it's the probability density for momentum, right? So there's kind of a parallelism between position and momentum, right? That the wave function, magnitude squared, is the probability of finding the particle at a certain position. And the Fourier transform of the wave function, magnitude squared, that gives the probability for finding the particle with a certain momentum, right? And so these things are giving sort of complementary information about the position and the momentum of the particle, okay? That's a matter of Fourier transform from the wave function psi to the Fourier transform wave function phi. Okay, so those are three examples of this generalized statistical interpretation. Okay, so to sum up here, we could say we don't need separate rules. For, well, energy probabilities and position probabilities and momentum probabilities, right? That maybe earlier in the semester, it sounded like there were different rules to think about for energies and for positions. And I didn't even talk about momenta before, but now we can see it is all the same rule. Okay, that this generalized concept encompasses all of these things about what's the probability of what happens in a measurement, okay, what you get in a measurement. Okay, now there's one more interesting subtlety of measurements in quantum mechanics that I need to also say. That's really important. That is what happens after a measurement. So what I just told you is the probability of getting some result when you make a measurement, okay? But there is a subtlety then about what happens after that measurement, okay? So if you measure some observable Q and you observe the value, so it's one of the values on the list, so you observe the value Qn, okay? Then the wave function changes to Fn. So the wave function is modified by the measurement, okay? That is a special concept in quantum mechanics, okay? That the wave function after the measurement is not the same as the wave function before the measurement. Okay, before the measurement, the wave function was psi is some combination of Cn, Fn, okay? Now you measure and you get one of the values on the list. You get Q13, okay, where 13 is, Q13 is the 13th number on the list, okay? Then after the measurement, psi equals F13. And this works for 13. It works for any number there, okay? That when you make a measurement, the wave function changes to the function that corresponds to the value that you measured, okay? And the word for this is collapse. Okay, people say that the wave function collapses onto F13 or whatever F corresponds to the measurement that you made. Okay. Now, this is a weird concept in quantum mechanics that does not really have an analog in classical mechanics, but it does have an analog in classical optics. And so let me try to explain the analogy with optics, and maybe that will make this seem less crazy. Okay, so I'll say for the analogy with optics, okay, so suppose you want to measure the polarization of light. So you guys have studied that light has polarization, right? That was in what, University Physics 2? Is that where it comes in, or in E&M? Maybe both of those things, okay? So you know that light has polarization, right? Which is some vector perpendicular to the direction of propagation, right? And so you know that if light is propagating this way, then it could have an electric field, which is in this direction, right? Oscillating up and down in this direction. So, or it could be oscillating up and down in that direction. That's another, or back and forth in that direction, right? That's another possibility. There are also more complicated things about circular polarization and elliptical polarization, but I'm not going to talk about that now. Okay, so suppose you just want to find out, okay, is light, here's light that's propagating in the X direction, and it might be polarized in the Z direction, or it might be polarized in the Y direction. Okay, and so you want to find out what it is, okay? And so you could figure that out by putting in a polarizing filter, okay? So suppose you put in a polarizing filter here that is aligned in the Z direction, okay? So this is a polarizer in the Z direction. Okay, and then if the light is polarized in the Z direction, it gets through, right? If the light is polarized in the Y direction, it's blocked. It doesn't get through at all. Right? Now, the light might be polarized in some other diagonal direction, say like this, okay? If the light starts off polarized in the diagonal direction, then some of it gets through with a reduced intensity, right? But after it passes through that filter, it is changed, right? That after it passes through that filter, it is now polarized in the Z direction. Okay, so afterwards, it's definitely polarized in the Z direction, right? So before passing through the filter, it maybe is partially polarized in the Z direction and partially in the Y direction, but after it's completely polarized in the Z direction. Okay? A quantum mechanical measurement is like that, right? That before the measurement, you might have a combination of a quantum state that is, some mixture of state 12 and state 13 and state 14, okay? But if you make the measurement and you find state 13, then after the measurement, you have just state 13. You don't have anything else. So it's like the output of this filter. And one other analogy with the optics is that, if you are doing an optics experiment, you can have a sequence of one filter and then another filter and then another filter, right? And the filters, they don't have to be parallel to each other or perpendicular to each other. They might be tilted a little bit, one rotated compared to the other, okay? So if I try to draw one like that, okay, I'll make another filter here. And this is, I don't know, maybe at a 45-degree angle or something like that, okay? And so here, let's call this a polarizer in the direction of y hat plus z hat over root 2. Okay, so that's the 45-degree direction. After the light passes through that polarizer, it will be polarized for sure in that 45-degree direction. Okay. So the polarizer is affecting the light, right? It's forcing the light to be aligned in the direction that comes from the way the polarizer is aligned, okay? And so the same thing is true if you have a quantum mechanical state, okay? And so that means, you could say in the beginning, you have a state psi, okay, which is something that is arbitrary. It is not necessarily an eigenfunction of anything, right? It's just any old state, okay? But then if you measure the energy, then after the measurement, you get the wave function that has to be in one of the energy eigenstates. Okay, and then if you measure something else, if you measure position, then right after the position measurement, you will have a position eigenstate. Eigenstate, singular, okay? And so each measurement is like the light passing through a polarizing filter, right? That you get something which is an eigenstate of the quantity that you just measured. Okay? Now, after you make a position eigenstate, it doesn't necessarily stay as a position eigenstate. It continues to evolve following Schrödinger's equation. Okay, and so at the instant after you measure position, it comes out as a position eigenstate. So that is, the wave function is spiked right at that position that you found. Okay, so right after you measure the position, the particle is exactly at that position that you found. Okay, and then as it continues to evolve, it continues to evolve following Schrödinger's equation. Okay, and so you could say the position eigenstate, the spike that you have right here, that's a new initial condition for Schrödinger's equation. Okay, and so this is now your new initial condition at some time. Okay, and then it feeds into Schrödinger's equation, and Schrödinger's equation tells you what will happen in the future after that instant. But this idea of sequential measurements is really a central thing in quantum mechanics. And so it's a point that you want to remember here. And one way to kind of visualize it geometrically is with the way I drew eigenvectors of different 2x2 matrices, right? So you remember when I was talking about 2x2 matrices at the beginning of the week, right? I said that matrix A has eigenvectors that are this and this, right? And then matrix B, I did it in blue, oops. And then matrix B has eigenvectors that are like this, okay? And then, you can express any old vector as a linear combination of the black vectors, or you could express any old vector as a linear combination of the blue vectors, right? You take your choice, right? So it's like that with Hermitian operators, right, corresponding to observables, except it's infinite dimensional instead of two-dimensional, right? But when you make a measurement of A, you are then forcing the state of the particle to be one of these black states. It will be this, or it will be this after the A measurement, okay? And then if you measure B after the B measurement, it'll be one of the blue states, this or that, okay? So the same way that the list of eigenvalues, that's the menu of possibilities for what you might get in a measurement, okay, the result of the measurement. And then the list of eigenstates, that's the list of possibilities, the menu of what can be the state immediately after the measurement of that thing. Immediately after, not forever after, but immediately after. And then it's the new initial condition. And then it feeds into Schrödinger's equation. Okay, so that's kind of the concept of a measurement in quantum mechanics, which I wanted to try to emphasize. And I will have a problem about that on the next homework, but I have not posted the next homework yet. Probably on Monday, I'll post the next homework. Okay, I've been talking about that for a little while. Any questions, anything about this? I know it's kind of a weird thing to talk about, but hopefully the optical analogy will be at least a little bit helpful for that. All right then. So that is one of the applications of this Hilbert space theory. Okay, and so it is to show you that that the probability rules work for any observable, right? That they work for energy or position or momentum, or in a little while, we're going to get to angular momentum, and they work for that also. Okay. Now, I want to get into a second kind of application, okay? And that is now the generalized uncertainty principle. Okay, so you know that we have talked about the uncertainty principle for position and momentum, right? And so I'll say we have seen there's this relationship between the uncertainty in X and the uncertainty in P, that this has to be greater than or equal to H bar over 2. Okay, so now, what if we want to generalize that, not just to position and momentum? Okay, so I'll say, suppose we have any two observables. Let's just call them A and B. Okay, so one example is A is position and B is momentum, but it could be something else. Maybe one of them's energy or angular momentum or anything. Okay, and then the question is there an uncertainty principle? Is there an uncertainty principle for the uncertainty in A times the uncertainty in B? Okay. Maybe, maybe not. We have to find out about that. Okay, so want to say, what is the relationship between the uncertainty in A and the uncertainty in B, and how does that depend on mathematical properties of these two operators, big A and big B? Okay, so this is actually kind of a few pages in my notes to work this thing out. I'm trying to decide if I actually want to go through all this. Yeah, I guess I will. It might be interesting for some of you. If it's not so interesting, you can just fast forward me. So, okay. So, yeah, this is going to be a proof, which is at least half an hour, but you can fast forward if you just want to get to the end. But no spoilers. Let's let this, for people who care about seeing how it works, let's go through it all. Okay, so the question is, what can we say about the uncertainty in A and the uncertainty in B? Okay, so first of all, we know the definitions of uncertainties, right, in terms of the expectation values, right? So if we are in a state psi, okay, there is an uncertainty in A. And the uncertainty in A is given by sigma A squared, which is the expectation value of A squared minus the expectation value of A quantity squared, like that. And that is equal, another way of writing the same thing is the expectation value of A minus average A squared. And this first expression is the one that we usually use for calculations, but this expression is the one where we started the derivation, and I'm sure at least once more in the semester I've used this sort of thing. So this is kind of familiar to you also, right? I think so, okay. All right, so this uncertainty, okay? So let's work that out using operator stuff, okay? So this uncertainty in A squared, so in the state psi, I could write this as the inner product of psi with the operator A minus average A squared acting on psi. Okay, this inner product is the expectation value of this operator in the state psi. Okay, now I can notice that this operator, the thing in parentheses, A minus average A, is a Hermitian operator. Okay, and that works because, well, this A by itself is a Hermitian operator because it's an observable. And the average, this is some real number. And so the sum or difference is also a Hermitian operator. Okay, so A minus average A is a Hermitian operator. Okay, so because it is a Hermitian operator, we can move it to the other side of the inner product. All right, that's one of the things we learned about Hermitian operators. Okay, so I have two of these operators over on the right side. Let's move one of them over to the left side. Right? So we get that this uncertainty is A minus average A acting on psi. Inner product with A minus average A acting on psi, like that. Okay, so now this A minus average A acting on psi, okay, that is a function. I'll call it f. Okay. So we know that A acting on psi, it's an operator acting on psi. It produces another function. Okay. Average A times psi, that's a number times psi. It's also a function. So the difference between those is yet another function. I'll call it f. Why not? Okay. So this is the inner product of F with F, where F is A minus average A acting on psi. Okay, now the same thing works for B. So I'll say, similarly, the uncertainty in B squared is the inner product of some G with G, where G is B minus the average B acting on psi. Okay, so now that tells us that the uncertainty, the product of the uncertainties squared, so sigma A squared times sigma B squared, that is the product of the inner product of F with F times the inner product of G with G. Okay, now when we have inner products like this, there is a mathematical theorem for these inner products, which is called the Schwarz inequality. Let me tell you what it says, and then I'll tell you why it's reasonable. Okay, what it says is that this inner product, this product of inner products, right? F with F times G with G, this is greater than or equal to the magnitude of the inner product of F with G squared. Okay, so why is this reasonable? Well, I'll show you an analogy with dot products. As I told you that an inner product is a generalization of a dot product that you've learned about for 2D vectors or 3D vectors. Okay, and so if you think about this as dot products, then that means this is saying that the F vector dot F vector times G vector times G vector is greater than or equal to F dot G magnitude squared. Okay, and then you could translate this into more geometrical notation. You could say F with F, that's the magnitude of F squared. And G dot G, that's the magnitude of G squared. And on the other side of the inequality, we know that F dot G, that's the magnitude of F times the magnitude of, times the magnitude of G times the cosine of the angle between them, all squared. Okay, and so this is saying that F squared times G magnitude squared is greater than or equal to magnitude of F squared, magnitude of G squared times the cosine squared of theta. All right, and so if we divide through by magnitude of F squared and magnitude of G squared, that's saying that 1 is greater than or equal to the cosine squared of theta. Well, that's true, right? You know that the cosine squared of any angle is between 0 and 1. Okay, so it's true for dot products. Okay, the Schwarz inequality is true for dot products. And it is also true for inner products in general. Okay, so if you believe the Schwartz inequality, which you should, okay, then what we have so far is that the uncertainty in A squared times the uncertainty in B squared is greater than or equal to this F inner product with G magnitude squared. Okay, so this is some complex number. Okay, so the inner product of one state with another state is a complex number. Let's call it Z. That's a good letter for a complex number. Okay, so this is some complex number magnitude squared. All right, so this is Z magnitude squared. Okay, so now the magnitude squared of Z, that, here, I'll write it down. The magnitude squared of Z, that's equal to the real part of Z plus the imaginary part of Z. The real part squared plus the imaginary part squared. Okay. Now, for sure, this is greater than or equal to the imaginary part of Z squared. This is a weird part of the proof, that it does seem like it's somehow throwing away information, but yeah, okay. For sure, this is true, right? The real part squared plus the imaginary part squared. This is one square plus another square, and so it's certainly bigger than the second square. Okay, so that's true. Okay. Now, what is this imaginary part squared? Okay, this is the imaginary part of Z is 1 over 2I Z minus Z star squared. Let's see, maybe, I don't know if this is clear or not. Let me clarify it, if not, okay. So if Z is the real part of Z plus I times the imaginary part of Z, right? And Z star is the real part of Z minus I times the imaginary part of Z. So if I subtract those two things, I get Z minus Z star is 2I times the imaginary part of Z. Okay? And then I'll divide both sides by 2I. Okay, so the imaginary part of Z is Z minus Z star over 2I. Okay, so if we put these things together, what do we get? Okay, we get that this product of uncertainties squared is greater than or equal to 1 over 2I. And so that's F inner product with G, right? That's the complex number Z, okay? This minus its complex conjugate, like that. That difference divided by 2I squared. Okay. Now, one thing that you remember about inner products is that the complex conjugate of an inner product is the same as writing the inner product in the opposite order, right? So the complex conjugate of inner product of F with G is the inner product of G with F. Okay, so that is sigma A magnitude squared, sigma B magnitude squared is greater than or equal to 1 over 2I FG minus GF squared. Okay, so now we want to analyze these inner products, right? And what's the difference of these inner products written in two different sequences? Okay, so let me try to simplify all of that. Okay, so here, I'll write it on another page. The inner product of F with G that is, let's remember what F is. F is A minus average A acting on psi. Okay. G is B minus average B acting on psi, like that. Okay, now you remember I said A minus average A is a Hermitian operator. Okay, so it can fly to the other side of the inner product, right? Like the god Hermes. Okay, so it can fly over there and act on the thing on the right side of the inner product. So this is equal to psi, say, A minus average A acting on B minus average B acting on psi. Okay, so now let's remember about how operators work, right? That here, the psi, that's the input into B minus average B, okay? And then the output of that goes into A minus average A, okay? So let's work out these things. I'm going to expand it in more detail. Okay, so this is okay. So I'm going to work from right to left. Okay, so here this is B psi minus average B times psi. Okay, that's what happens when psi goes into the first thing on the right, okay? And then A minus average A acts on that. Okay, so now this combination of stuff, that's the input into A minus average A. So this is now, the operator A acts on both of those things, okay? So we get A, B, psi, okay? Minus, now the operator A acts on average B times psi. Average B is just a number, so it factors out. Okay, so it's average B times A acting on psi. Now I have to subtract off average A times each of those things. So minus average A times B acting on psi, and then average A times average B times psi, and the two minus signs cancel each other. So plus average A times average B times psi. Okay, so all those things are on the right side of the inner product. Okay, now this, I'm going to expand this inner product, okay? So here I have a combination of 4 terms on the right side of this inner product. So if I expand this, okay, the first term is psi inner product with A acting on B acting on psi. The second term is the inner product of psi with B times average, with average B, this number, times average A acting on psi, right? So I'll factor out this number. This number is average B. And then the inner product of psi with A acting on psi. Then let's do the next term. Okay, so I factor out average A, and I have the inner product of psi with B acting on psi. And then in the last term, I'll factor out average A, I'll factor out average B, and what's left is the inner product of psi with psi. Okay, now we can actually simplify some of this stuff. Okay? For one thing, the inner product of psi with psi, that is 1, right? Because psi is some normalized state. Okay? Then here, where we have the inner product of psi with B psi, that is the average B. Here, where we have the inner product of psi with A psi, that is the average A. Okay, and then this thing, what is this thing? Well, I guess we could call this thing the average of AB. Like that. Okay, so this now is all equal to the average of AB minus average A times average B, minus another factor of average A, average B. Oops. And then the last term is plus. Hey, my pencil doesn't write on the bottom. Pencil doesn't write at all. Oh, there it is. Keeps coming in screwed. Okay. Plus another average A, average B. Well, all right. So these last things cancel each other. So F with G, inner product, is equal to this difference of expectation values. All right. How am I doing on time? Oh, I'm out of time. Yikes, I'm out of time. Oh no. And I was almost getting to the exciting conclusion too. Well, this will just be a cliffhanger. Okay, so you guys will have to wait until Monday to find out what is the uncertainty principle for A and B. Okay, well, so be it. I will stop talking for now. And of course, I'll answer questions if anybody has any. And in any case, I will stop for the week and we'll finish this up on Monday. Okay, so see you all then. Have a good weekend. Bye.